welcome again to another great video. So we are still on the topic of electromagnetism. In this case, we're dealing with a past paper problem from November 2022. It was a Gauteng, right? Now, in this particular problem, what we have here is we're told that there's a solenoid, which is the one on the left, and then there's a power magnet on the right. So the power magnet is suspended on a light inextensible string, and then it is allowed to move freely. Inextensible just means the string does not stretch. So if you've ever seen a rubber band, you can extend that thing by stretching it. This string won't do that, it won't stretch. And then allowed to move freely means if ever there's something that's a stimulus to this magnet, something with enough magnitude to move the magnets will move. Either if it has to spin or if it has to swing left or right, it will move. If whatever force or disturbance on the magnet is good enough, let's just say it's good enough, or it has enough magnitude, right? So yeah, it's not fixed. It's not like it's nailed onto this thing so that it doesn't move. It's just it can swing, it can rotate, it can do whatever movement, right? So now yes, that's the information we're given. And then so this is our power magnet, this one, power magnets. We are stating the obvious here, I know. And then this is our solenoid. Remember, a solenoid can also become a magnet if you run current through the solenoid, okay? So I think that's why we have that battery there. So now we are asked to state Faraday's law of electromagnetic induction in words. So if you remember, what we always say is the basic idea of Faraday's law of electromagnetic induction is that if ever you have a conductor and a magnetic field, if you move one of the two, obviously you can't move the magnetic field, so you are moving the magnet, which is the one that produces the magnetic field, right? So what happens is if you move either the conductor through the magnetic field, there will be a magnetic flux, right? But it will change because you are moving either the magnet or the conductor. So that change or that rate at which that change occurs, right, that change in magnetic flux, the rate at which that change occurs will then now affect how much EMF you induce in the conductor. Because remember, first of all, for EMF to be induced in the conductor, it's because of that change in the magnetic flux. So the change is a result of you moving the either the magnet or the conductor. So now that change will induce an EMF in the conductor. But then what will affect the magnitude of the EMF in the conductor is the rate of that change. So how fast is it changing is what affects the magnitude of. So that's basically what Faraday's law of electromagnetic induction says. Okay, so yeah, that's what you would state. So yes, the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux. Okay, so that's how it works. Now let's go to 6.2. I will write 6.2 here. So with 6.2, we are asked in which direction will the suspended magnet move when the switch is in the circuit of the solenoid is closed. Okay, so right only towards, away from, remains at the same place. Explain why this happens or why this will happen. So let's go to our solenoid. We are being told that this switch will be closed. Remember, if it's open, there won't be any current flowing in the solenoid. So the current must flow throughout the conductor, right? Throughout the coils. Like that, like that, like that, and then back like that, and then it repeats the cycle. But this can only happen if the switch at S is closed, because currently it is open. So it's as if you just have water coming and it gets to this gap, it just spills, runs there, instead of continuing on the road or on the passageway or whatever. So once you close this, it's like a bridge now. You allow the current to flow through the entire circuit. Okay. So that's what they did here. They closed this switch. So now it's closed. So current will now start flowing in this circuit. But another question now comes, where will it start and where will it be going? So if you remember in your grade 10, you call this a cell, right? So the way current moves in this battery, it will start at the back of the longer line. If you check, this thing has longer and shorter lines, right? Longer line, shorter line, longer line, shorter line. So a single pair of these lines is called a cell, if you remember correctly. Longer line, shorter line. So the current always exits at the back of the longer line. That's what you can think of to always remember. Right, so once we have that, we are almost done. So now it means this current will keep going here, and then it will go through this coil, go again through this coil, this loop, and then go in there, and then come back again here to finish the cycle. And then it keeps doing the same thing over and over and over again, probably until the battery runs out. Okay, so that's what happens. Now remember what we said. As soon as you pass current through the entire solenoid, what you get is a magnet. The solenoid becomes a magnet. So it means B and A will have polarity. By polarity, I mean B will either be a north or a south pole. A will also either be a north or a south pole, because now it's a magnet. This whole thing is now a magnet. So how do we know if A is a north or south and B is a north or south? How do we know? So that's where the right-hand rule comes in now, if you remember. So in this case, we have that. So the right-hand rule, usually we would be given either the direction of the magnetic field, magnetic flux, or we would be given the direction of the current, and we have to find the direction of the magnetic. So in this case, we have the current. Remember this one that we drew here. So if we use our right hand, let me draw our right hand here. You take your pen and you hold it such that your fingers are curling in the direction of the current, because we're already given the direction of the current from how we analyzed the circuitry of this thing. We can see that our fingers would have to curl that way, like this, right? So our fingers are curling into the page, because that's where the current is flowing in our solenoid. And then remember, then the thumb will ultimately or automatically point in the direction of the north pole of the magnet. So it means point A will be our north pole. Since a magnet has two poles, a north and a south, so since A has already taken our north, it means B would have to be our south pole, right? But remember, these poles, because this is a solenoid, they can change almost at any instant. They are not fixed. So if now I change the situation where now maybe I reverse the direction of current, you might find that B changes to be a north pole instead of a south pole. So don't always think of it as a fixed thing. it's always dependent on the situation that you have. Sometimes I can be taking a magnet, that bar magnet, and I pass it inside the solenoid. You might find that when the magnet is still here, let me throw it. This is just outside this exercise, but it's worth noting. Let's say I pass the magnet and it's still here. When the magnet is still at point A and this side of the magnet is facing, you see, north pole of the bar magnet is facing the north pole of the solenoid. So according to Lenz's law, of course we would have to determine what this guy would be. So if I'm pushing it in, according to Lenz's law, point A would have to be, yes, a north pole. So this one is fine. It would have to be a north pole because the induced current inside will generate a field that will want to repel this bar magnet. So this thing would have to be a north pole. So if I come here, as the magnet is now moving away, so let's say I don't change the bar magnet configuration, it's still SN. So now S is facing S. But it doesn't mean this is still an S, this one. This one is dictated by the condition. So I'm moving the magnet away, right? You will notice that this will change to be a north pole instead. That means that one would be a south pole at the state where I'm pulling the magnet away, because it has to attract the magnet back. So the point I'm trying to drive is it's not always fixed. It's not like a bar magnet. In a bar magnet, you can't change the polarity. But for a solenoid, it changes almost every instant depending on the situation. Okay, that's one thing I want you to know. Don't fix it. It's not like a bar magnet. Don't think of it as a fixed thing. So now we have that. We know that A is north, B is south. So if A is north and B is south, check. So now what essentially happens is, if this is our solenoid, let's draw our solenoid as a bar magnet. It means I have north, south. And then let's draw our bar magnet now. It means now I have, this is my bar magnet, north, south. I just drew the bar magnet as it is. So check. These two poles are facing each other, right? So these are unlike poles. So do you think there will be attraction or repulsion? So since these are unlike poles, there will be attraction. Okay, so the bar magnet will be attracted to the solenoid because the bar magnet is allowed to move freely. So we can assume that it's the one that will move towards the solenoid. So we can say our answer here is towards. Why? Because at point B, the polarity at point B is a south pole, and as a result, unlike poles attract. Since point B is facing the north pole of the bar magnet, there will be attraction because those two are unlike poles. So that's your reason. That's why this will happen. So that's how you would get that 3 marks. First, the bar magnet will move towards the solenoid because south and north attract. These two are unlike poles. So yes. So let's write our answer. First we say towards. So like I said, we said this thing will move towards, right? And then the reason for this is because the flow of the current will produce a magnetic field such that the polarity of this magnetic field is a north pole at A and a south pole at B, right? And then since it's a south pole at B, it will then attract the north pole of the magnet. Thus the magnet will move towards the solenoid. It seems like this thing was longer to write, but you can always summarize it as long as you have all the important keywords or key points rather. All right, so yeah, that's our reason. It looks like a lot of English, but I promise it's not. As long as you understand the basic fundamental reason why you would observe something like this, you can always find a shorter way of explaining it. So I try to be as elaborate as possible in this explanation. So yeah, this is what would happen nonetheless. Now, name 3 changes that can be made to the system on the left to increase the effect on the magnet. So essentially what they're asking you is, how can we increase the magnitude of the induced EMF? It's another way of asking it. So, but now whenever you're answering questions like this, I know there's that list, which is what, increase the number of turns, increase the speed, and so on. You must bring the answer to the current situation. For instance, one of in that list of things that you can do to increase the induced EMF, right, is you would have to increase the speed of the coil. But here the coil is fixed, so you can't mention that. It won't work, because in this particular situation we are not using speed. So you must think of it in terms of this situation. Now we are trying to increase the force of attraction, right, between the solenoid and the bar magnet. How do we achieve this? So we can use a stronger magnet. For instance, this one, the bar magnet, we can make it a stronger magnet, right? Another thing that you can do is you can use, in this case, you can increase the number of coils. Yes, that counts. You can increase the number of coils, and also you can also increase the current. Yes, I think that one would work. You can increase the current by probably using a bigger battery. Right, so those are the acceptable ones. So you can't come and use speed or theta, because theta, I remember, is one of those things. So here we were mostly focusing on increasing just that magnetic force that made this bar magnet to move towards the solenoid. So all your reasons would have to feed onto that. All your reason would have to justify how we can increase that magnetic force. All right, so we said, first of all, increase the number of turns. That's one good one. Another name for turns is loops. All right, some people prefer using loops, some prefer using turns. And then we said we can also increase the strength of the bar magnets, use a stronger bar magnet, right? And then we can also increase the current on the conductor. Increase the current. I keep saying conductor, but most people would use solenoid. Solenoid is still a conductor. Let's use solenoid. In this solenoid. So increasing the current in the solenoid will increase the EMF, right? So now these are the things that you would mention. So it's just you have that list, and now what you do is you bring it to this particular context, to this specific application, right? So this is all I have for you for today, and I will see you on the next video.